information that we got in for the last couple of weeks. So all is well. It's the eve of the weekend and the end of the week, and I hope that it starts getting warmer because we're getting into May and it's 50 degrees. So that's utterly ridiculous. So anyway, we'll get there. Who likes summer? I do. You guys like summer? Or are you cold weather? You're like, I don't know. Not the 90-degree heat. Hey, Kristen. Awesome.
Hi, sorry, I was doing laundry real quick.
Oh, please, you're fine. You're fine. I was just telling everybody I put a couple of extra pictures and kind of redid the PowerPoint just so it kind of cleans it up a little. I'm going to resend it out. It's the same information, just prettier. And then let me know. I know I sent out all the videos on Monday, so any issue, just let me know if you can't open them. I need the IT people to help me.
Awesome. Thank you so much.
Oh, you're welcome. Okay, so
I don't think I got the videos.
You didn't, Bree? Okay, I'll send them all over tonight.
I didn't see them when I went through my email.
No worries. Let me resend them tonight, okay?
Thank you.
You're so welcome. You're so welcome. Okay. Now we talked about, so now there's just, when I send this, you'll see like the pictures that my Italian hands kind of do on the actual what an atom looks like. I broke it down in here. Properties, characteristics, the X-ray tube. Here you go. What the machine looks like. And then I broke it down, and I believe here's the glass tube now. So we should have a good picture in mind of what everything looks like. Control panel, X-ray production that we talked about. And now this is all new stuff right here, right now. So we're going to start this evening with the types of radiation, and then we're going to get into a lot more definitions of why these definitions are important when we're looking at the quality of the x-rays so that we know that they're diagnostic for the provider. So making sure that these items are going to be a lot of information that's on, if you're taking the test or learning how to like look at x-rays, they would make more sense once this vocabulary and understand what they look like. So this is the start of all of that. So we know how electromagnetic radiation is harnessed, right, from regular electricity. It goes through the X-ray machine. The electrons collide inside the glass tube. 99% is generated as heat. 1% comes out as electromagnetic radiation, which is our most penetrating part of the radiation that's coming through. That beam of radiation or that ray of radiation that's coming out of the X-ray machine has many different names to it. We can call it primary radiation. We can call it primary beam. We can call it central ray. Okay, so any one of those names, when you hear it, you know that's the first kind of launch of the electromagnetic radiation, the X radiation that's coming out. So it is the first thing that's coming out of that machine. So the types of radiation, there's going to be essentially two main types and then one auxiliary here. So the first one is primary radiation. That's the original radiation beam coming from the target or the PID. It's the most useful beam. It's also called primary beam. It is the most penetrating, okay? So that has the most amount of power. The moment that that primary radiation or primary beam hits matter, hits the target, the second it touches the target, it's called secondary radiation, okay? So that's when the primary beam interacts with matter, whether it's us, whether it's a lead apron, whether it's wood, whether it's a book, it doesn't matter. But for our purposes, the moment that the primary radiation interacts with our tissues or the patient, it becomes secondary radiation. Now, a form or the auxiliary of secondary radiation is scatter radiation. Scatter radiation occurs once that main beam, again, secondary radiation touches matter. The moment it touches matter, it deflects, and that's the deflection of that radiation, that scatter radiation. That's what we're going to call scatter radiation. Forms a secondary radiation occurs when beam is deflected from its path through the interaction of matter. It deflects in all directions. This is why we wear lead aprons. This is why we don't stand in front of the X-ray beam or in front of the X-ray tube head. This is why we're 6 feet away on a right angle outside the room when we're taking these x-rays so that we do not get hit with scatter radiation. So the 3 types of radiation is primary radiation, secondary, scatter. Primary is the initial, secondary is the moment that initial hits the target, and the moment it deflects, it's called scatter radiation. Perfect. Good? Types of radiation, easy peasy. Now, these 2 definitions and are a really huge important piece, and when we get into anatomical landmarks next week, super huge. So radiolucent and radiopaque. Does anybody know what radiolucent image would be? Garson. I just put you on the spot. I know you look at x-rays all day. I'm just playing with you. You're fine. You're fine. Everybody gets these 2 mixed up every day, so it's all good. It's all good. You're the only one out here. So
Well, I'll be honest.
yeah,
I'll be honest.
shoot.
Since I'm on the orthodontic side now, I don't get to see X-rays as much as I used to on the general side.
Oh my God, that you're perfectly fine. I'm just calling on because you're smiling and you're always so happy, and we just love to hear your voice. It's all good. It's all good. So I'll go through the definitions. No worries. So let's talk about radiolucent first, okay? So radiolucent images or characteristics are going to be described when we describe body structures that the radiation can easily pass through. There's going to be no hindrance, no bouncing really off of. It goes straight through. Those are going to come. Radiolucent is another name for like a dark area or black area, okay? It's empty space. Let's put it that way. So when you have radiolucent, means dark, or it's going to show black or very dark, right? It's going to be air spaces, like in sinus cavities. Our sinus cavities are on our maxilla, are open air. It's how we breathe, right? It's an open airway. It's totally empty space, air space. So there's no restriction. That primary beam goes straight through. It's going to show the sinus as a black space, okay? Radiolucent. Abscesses, infections, all are going to be radiolucent. Decay, whether it's recurrent decay, new decay, doesn't matter. If it's decay, it's going to go straight through. Why? Because decayed enamel or dentin, decayed tooth, there's nothing there. The bacteria ate it away. So it's leaving the decay there, but a solid part of the tooth is gone. So again, it travels straight through. So decay will show up black. The pulp of a tooth, which is the total inside of the tooth where your nerve and your blood supply is essentially, it's just light tissue, again, showing black. So makes sense. So a couple of big portions here to just, again, review. Radiolucent means dark images or black images on the x-ray. It's going to show airspace as sinuses, abscess, like infection, decay, as in, cavity, and pulp, which is going to be the center, the blood supply, and the nerve supply of the tooth. Does that make sense? So far, so good. Good. Now, on the other end of that, if that is black, radiopaque is going to show white or a light gray, okay? So these are structures that radiation cannot pass through. It's going to bounce off of, okay? It's going to create that white or light gray area. And there's going to be a lot of examples here, guys. So additionally to what I wrote here. So like write this down, okay? So bone, all bone will show up like a light gray. Metal restorations are going to show up white. Implants are going to show up white. Root canal teeth, what we call endodontically treated teeth, where they have like this filler inside, that's going to show up white as well. Metal restorations are like crowns, amalgam fillings, things like that. Even composite tooth colored restorations are going to show up like a whitish light gray. Fun fact, enamel, the outside layer of your tooth, shows up a whitish light gray on the picture. The second layer of a tooth, which is called dentin, will show up a whitish light gray on the picture as well. So those are solid, solid structures. So we can say solid structures, guess what they are? Radiopaque, right? And anything solid will show that white or light gray. Does that make sense? And did everybody list those? Do you need me to repeat the structures that it needs for radiopaque? Everybody got them? Cool. Good, good, good. And if not, you can always email me or text me on the side. No big, no big, big. Okay. So with that being said, I want to mention two more words that we're going to define in a moment. The next word we're going to define again is called contrast and density, okay? As far as what we're talking about now. You see where it says characteristics of an X-ray beam? Cool. I know the other day we talked about characteristic of electromagnetic radiation. This is different. That's the actual radiation itself that we're characterizing. Like it goes in a straight line, it's in waves, we can't touch it and taste it. That's radiation. These are characteristics of the beam itself, meaning how penetrating it is, how we get a good quality picture. That is what I'm talking about when we're talking about the quality or quantity of picture. Like that's the characteristic I'm looking for here, okay, of the X-ray beam, not the radiation. I know it kind of gets confusing when you use the same types of wordage, but it's different things. So contrast, the definition of contrast actually means grayscale, okay? It's the grayscale. Well, what does that mean? Well, I'm so glad I have black and white on today because now you're going to see what contrast is, okay? So when we want something high contrast, that means we want the blackest of black and the whitest of white. And we want to be able to see the difference between the black and the white, just like my shirt and my jacket, okay? This has a high contrast. You can see my white shirt against the black or the black against the white. Very clear, very crisp. It's very defined, so that is high contrast. Low contrast would be the opposite of that. It would be all gray scale in that. Like I know that the contrast means the gray scale from white, very white to very black. Low contrast means the gray in between. let's say I had a gray sweatshirt on and like a dark gray sweatshirt and then a light gray t-shirt, very not crisp, right? Not high definition. You can't really see where one ends and one starts. Does that make sense? So, because gray is like it has different shades of gray, very hard to determine things different in that gray shade scale, okay? But black and white, you can see very crisp, clear images. Grayscale, low contrast, not clear enough, not a good quality. Does that make sense? Pretty much? Okay. But by definition, contrast means grayscale. So when we want high contrast, we want not a lot of grayscale. When we have low contrast, we have a lot of grayscale, okay? Now, density. Density can have two definitions. In this definition, when we're talking about characteristics of an X-ray beam, we're talking about the overall blackness of a film, okay? The overall blackness of a film. If we were talking about a human, a dense human, that means like bone structure. We talked about that. Children, like an average size adult or large size adult, that's different density. It would be have lower density, medium density, high density, or thick density kind of thing. Dense, right? When you hear the word dense, it's like thick, it's solid. But when we're talking about X-ray beam and the quantity or quality, here we're talking about the overall blackness of a picture, okay? So that's what we're talking about now. Now, there's going to be three characteristics, so highlight these three and we'll define them. It's going to be a quality is a characteristic, the quality of the X-ray beam, the quantity of it, and the intensity of it. Okay, so three characteristics: quality, quantity, intensity. Well, what does that mean? When we talk about quality of an X-ray beam, that means we want the best, cleanest form of that X-ray beam that we get out. So we need the correct setting, the correct time, and we want to make sure that we have our machine itself is set up, the settings are accurate so that we can control the quality of the picture. Quality meaning it's very diagnostic, okay? We can diagnose well with it. Everything's clear and crisp. So quality is going to be described in relation here as energy or the penetrating ability of the beam. You keep hearing me say penetrating power, penetrating beam, penetrating. That means how clean or how much energy or penetrating power does that beam have to infiltrate the tissue and capture a nice image, okay? So the quality or wavelength are controlled by kilovoltage peak, KVP. We talked about that last week. So KVP controls the quality because KVP is kilovoltage peak, the penetrating power, the volts, the energy that is inside the machine itself. The more penetrating power, again, the shorter the wavelengths, right? The shorter the wavelength, the greater penetrating power, all of it, the more energy it has. So we're going to get that clean, crisp image. The range of KVP, now we do not have the ability to change that setting. As I said before, the factory already presets that amount of power that that machine creates or generates there, okay? So it's going to either be a range of 65 to 75 kVp setup or 85 to 110. All right, that's going to be on the higher side. So the low kVp, 65 to 75, and high kVp, which would be 85 to 100. Make sense? Those are the ranges, low, high. Great. Now, okay, so 65 to 75 kVp produce less penetrating x-rays and longer wavelengths. You're like, well, why are we have our machines set up to that? Well, because believe it or not, we can filter out those long wavelengths, right? And get the penetrating power from there, but we don't have to amp it, like gets all that penetrating power and have like a safety issue with it. It's like that, what is the best, the lowest amount possible. Again, just to go over density, overall darkness or blackness of an image. So when we change, let's say if we could change KVP, if we did, it could result, if we made KVP higher, it would result in a darker or denser image. When KVP is lower, it's not as black. It doesn't have that blackness. It has more contrast. It has a little bit more grayscale in it. Still good, but a little bit more grayscale in it, okay? Now, can anybody answer this question, just kind of like think it out loud? Do you think I want a really dark picture, or would I rather have more on the grayscale side? Anybody?
Grayscale?
Grayscale.
Grayscale.
Perfect.
Oh.
And the reason why I want a grayscale is I at least I want to see white and I want to see black, but I want a little gray in between because I want to see the contrast between the different structures, right? If I had an overall black film, could I get all the details out of that? No. No. Make sense? Does that make sense? Bree, does that make sense? Oh, I think she's frozen. Okay. Sorry, she froze up. She froze up on me. Okay, so does that make sense to Mia, Kristen, Mandy, Gerson? Good. Okay.
Yes.
Yes.
Okay, all good. I know, I know. And if you're driving, Kristen, don't you go on speaker. I know, I get it. No worries. To Mia, does this make sense? Because I know this is it's like newer kind of concept for you. Do you have any questions? No, I'm just not calling out on you. I just want to make sure you understand.
No, no, no. Honey, as far as questions go,
I don't have any questions. I'm just trying to catch up with you, basically.
Oh
I'm
my
trying to
God.
write all this down on pen.
Oh my God. If you need me to slow down, please do, and I can repeat anything.
No. Honestly, I'm just screenshotting and sitting up here trying to copy.
No worries, no worries. I get it. So, so quality is controlled. KVP controls the quality, which is the penetrating power, that higher energy. That's what we want. We know the ranges now. 65 to 75 are the lower range. 85 to 110 are the higher range. Typically, you'll see our x-ray machines, our regular intraoral x-ray machines, the ones we take pictures in the mouth, are going to be in that 65, 70 range. And a lot of times our extraoral oral cans, our CBCT scan, they're going to be in that higher, the 85 to 100 or even higher KVP range, okay? Just because it's outside of so it needs to have more penetrating power, more volts, more energy to use. So the next characteristics are quantity. Our quantity is measured by amperes. Oh, milliamperes, your MAs. We talked about that. So the quantity, the number, milliamperage is going to equate the number of electrons, that are in everything. You good, Bree? You froze there for a minute. Oh, good, honey.
I got kicked out. It like
I
kicked
know.
me out, so I had to go
I
back in.
I saw. I'm like, everybody's having like internet things going on. I'm like, oh my god, it's the bolts. It's the gremlins in the thing. Yeah, I didn't go over anything crazy, so I'll just do it again. So the next characteristic, quantity, that's a number. It's measured by milliamperage, MAs. Okay. And it's the number of electrons, that are going to hang out in that cathode, right? In that negative cathode, that negative area in that glass X-ray tube. It hangs out there. The moment we turn that machine on, those electrons come on in and chill out there. It's a number, how many? A range for milliamperage or MAs is 7 to 15. 7 is usually the go-to. It's going to give us the best contrast, the best look of the picture. And usually a setting anywhere above 15 is not going to be recommended. So the range is 7 to 15. 7 is the most favorite, and it will give us that high contrast portion of it. Now, intensity is going to be the third characteristic, which is going to be a combination. So how do we get the best intense or best looking diagnostic X-ray that we can? Well, it's going to be a combination. We're going to use a combination of milliamperage at the correct setting, our MAs, our quantity, our number of electrons, and it's going to be the KVPs. How much energy are we using? The quality, the penetrating power. So we're putting all of this together. Intensity is going to be affected by our KVP, our MA, how much exposure time we're going to use, and the distance from where we put the PID to the target. Okay, so we always want that PID, the X-ray machine, to go right up to where we're taking that picture, because we want to minimize that space, that length of time before that primary beam engages and hits the matter, hits our tissue. Okay, so again, intensity is a combination of all things. It's going to be quantity, MA, it's going to be quality, KVP setting, it's going to be the exposure time setting, and then the distance of our tube head from our picture that we're taking, our image sensor. Perfect. Now, again, I put the definitions here. Your contrast is black to white. It's shades of gray. It's known as the gray scale. The scale is called contrast. Density means overall blackness. It appears black in the air spaces, and then we see those really white areas of either restoration, bone, enamel. Gray are usually soft tissues. We know that density, the overall blackness, is going to be controlled by the milliamperage, okay? The quantity, the electrons, is going to kind of be the setting for that. Now, I have one little guy down here. It says
chemistry right now.
What happened?
I said you talking about neutrons and stuff. It makes me feel like I'm in chemistry right now.
Oh my God, I know. It's crazy. You know what? We're almost through it. I promise. We're almost through it. We'll get into the good stuff quick. You see my little slide here at the bottom? It says geometric characteristics. Okay. That means size and shape of things. So let's talk about the geometric characteristics. I may have to type this portion of it for you. For some reason, I'm not seeing where it should have come up, but I don't see it. So give me 3 seconds. And I will type it up really quick. Or read it, and then I will type it in here and get there for you. Okay, geometric characteristics. Why this didn't have it here, I'm going to put it in my little chat notes here. Can you guys see when I write chat notes? It's okay, right? So geometric
Yes.
characteristics are going to be sharpness. That's how, like, it's going to be defined as like high definition. If a patient moves, it is called penumbra. I'm going to put this defined here, penumbra. Penumbra equals blurry, which equals patient moving. So if a target moves, it's going to be blurry. It's going to be called penumbra. That means that we're not getting that high definition, that sharpness. So that's not great. There's going to be three things here that are important in order to get sharpness. And you could take a picture of this note here that I'm writing. So we have focal spot size. Let me explain what that is. Focal spot is inside the machine itself. It's in that target, that anode, where that target is, that's the focal spot. So when it is smaller, it is going to be a good focal spot. We want the focal spot small because it will give us a sharper, higher definition. So focal spot in the glass tube head in the anode portion, which is positive, we want small focal. Oops, learn how to spell focal spot. A large one will give us a blurry definition there, okay? The next is going to be something called film composition. If we were using actual film, we want fast film speed. We're going to talk about that in the next chapter or next session, all about, the film composition. The larger the crystals that are in that film, the faster the film, the sharper or how we get it. So film composition has a lot to do with that. And finally, it's going to be movement of a patient, movement of the sensor, the film, the machine. Any kind of movement is going to have that penumbra, the blurry. So we're not going to these are all going to affect the sharpness, okay? The next thing that we're going to look at here, so it's sharpness, and then it's distortion. I have no idea why this is missing from my PowerPoint here. So distortion means this. Every x-ray I take, the tooth itself has to be the exact size of what the tooth is in the mouth, okay? So when we have distortion, like the tooth is longer or shorter, fatter, that means something is distorted. We distorted it somehow. So distortion of tooth size and shape is not good. No good. Okay, we don't want that. We want actual real life tooth size in there. Okay, we'll talk about the fancy words for distortion in a little while when we really define that, but you'll hear me say two words, elongation and foreshortening. That is I'll just put it here. Elongation is a long tooth, so we don't want that. And foreshortening is a short tooth, and we don't want that. Okay, so those are going to be errors in distortion. The last thing is magnification. Now, in these digital programs we can manually magnify a tooth if we want to get into the nitty-gritty and see something, or move an x-ray around 3D and magnify things, and that's great. That's manipulation. But when we take an x-ray and it's magnified, it's fat, we don't want that. Again, we want this same tooth size and structure exact of what it's in the mouth on the picture. That has to equate. If it distorts in a magnified manner, we do not want that. We don't want that magnification. So we can control it on a screen, but when our X-ray gives us that, then we have a problem, okay? Now, a couple of notes to have here. I dived a little deeper and kind of cleaned up KVP, MA, what controls this, what controls that. So ideally, when we're taking x-rays, we would want to see that radiopaque, that real white of a restoration, a metal restoration or composite restoration, and really black of the pulp or sinus cavity, airspace. We do want some shades of gray and some great shades of gray in the extremes, between the extremes, okay? But we always want to see something really white in a picture and something very dark in the picture, very black, because then we know we have the true high contrast grayscale, and that's everything we want. Now, I put this little an example here that we'll talk through. So if I have a machine that has a high KVP in that 85 to 100, 110 range, it's great. It's going to produce more penetrating radiographs, which is fine. However, it's going to give us lower contrast, okay? And you're probably like, well, why? Well, we're going to discuss that. So if we're using a 90 kVp, which is that higher kVp range, it requires less exposure time. So that's a setting we can change, right? I can't, if our x-ray machine was 90 kVp and I can't change that, and I can't, the manufacturer won't let me, then, well, you're like, well, I don't really want that. I want to get a high contrast x-ray and a diagnostic quality. So what do you mean? What do I do? Well, I can lower my exposure time and I can lower my milliamperage, my MAs, the amount of electricity I use, okay? So what does that mean? If I have a lot, high kVp, high volts, high energy, I can reduce, or I want to reduce, exposure time as well as the amount of electricity we use, the amount of energy, the amount of electrons, MAs. High kVp, I can't change. What do? I lower my time and my MA setting. Does that make sense? High, I have to lower something. Now, the opposite is true. If I have a 70 kVp, which is lower, slightly lower, then I need a slightly higher exposure time as well as increasing my MAs. This mix, 70 kVp, low kVp, higher exposure time, higher more electrons, more milliamperage, that's beautiful. That's going to give me that very high contrast, that black and white, and fewer shades of gray. Perfect. Okay. So does that analogy, or as one is high, something we have to reduce, and then vice versa? Okay. Again, contrast, it some dentists like darker pictures for some reason, or some like lighter pictures. They let you know, typically for anybody in our practices, their standard, they want a high contrast. So you're going to see those really dark areas versus those really white areas all the time for them to diagnose. So they are pretty standard with that across the board. There's not a lot of differences between the doctors. Again, does that make sense how I said high kVp? I need a lower time and milliamperage. Lower kVp, I increase my milliamperage and my time. Any questions with that? Can I repeat any of that?
Can you repeat the last thing that you said as far as the high? Oh, wait, somebody put it in the chat. Oh, that's you, right?
Oh, can you repeat yourself to me? I'm sorry, I broke up a minute.
Yeah, the last I was writing down. I said the last sentence that you said is about high KVP.
Yeah, absolutely. So again, if I have a high KVP, like a 90 KVP setting, I need to lower both milliamperage, the MA setting, and the exposure time. I'm going to lower the exposure time. And that will give me it'll give me more shades of gray, which is fine, but it's going to give me a low contrast. Anytime my KVP is high, I'm going to just get a low contrast because it has that much penetrating power that the picture will be like it have an overall like darkness, that density to it. Vice versa, if I have a low 70 kVp, then I need to scooch up my exposure time and my MAs. I think I have a cheat sheet written out to me as well. I will send that tonight with these slideshows for you, okay? Cheat sheet.
Okay, thank you.
No problem. Sometimes seeing it in a different note taking helps as well. I know I'm saying it, but seeing it in different ways is helpful. Just, and I use arrows too. I'll say high arrow KVP, low arrow MA and time. So visuals will also help. Okie doke. Okay.
Okay.
I know it's a lot. It'll sink in. It's all new. We'll give ourselves grace. All good. It's like speaking a foreign language. We will learn it eventually. Okay, now density. So we're gonna kind of talk about density. That's the overall blackness, right? So we need to talk about that. The milliamperage, the amount of electrons, and the amount time given the exposure time will basically control the density of a picture, okay? So as KVP control, guys, this is important. I just want to highlight this. KVP controls contrast. Milliamperage or MA controls density, the overall darkness. What is a factor or what will also affect density, not just milliamperage, but the distance of the X-ray tube itself from the patient will also affect density, okay? We want it close, so that's what we want. The further away, the lighter we get, okay? If we were developing an X-ray manually with chemicals, how we do that, the time and temperature of what we do that, will also affect the density, which is the overall blackness. By overdeveloped, it's going to turn completely black. It's going to be too dense. I can't see it. It's not going to be diagnostic. And then again, the body size of a patient. Small child, average adult, those are all going to affect the density of a human will affect the density of the picture itself, okay? So that kind of helps you out in, it's like density equals density here in that aspect. So those are three factors that will affect density other than changing time and MA and the milliamperage. Okay, oh, here's my kid. Oh, look at me, guys. Here's my slide somehow and I went and typed it. Yay me. I knew I didn't miss it, weirdo I am. Sorry. Anyway, you have a copy of everything I typed up in that little box. Again, our three geometric characteristics: sharpness, magnification, and distortion. Again, sharpness is how crisp or how high definition, clear our images are. We don't want it blurry or fuzzy, called penumbra. We know the three issues that if that were to arise will affect the sharpness are focal spot, the film composition, if a patient moves, okay? Distortion is the second, and we know that is a change in size or shape of the image. It's going to either be excessive or insufficient. And those two words, elongation and foreshortening. And then again, magnification, if the image is enlarged when we want the exact size. So those are going to be the three geometric characteristics. It's basically size and shape, and we want the quality of the image so it's diagnostic. Cool, great. This we're going to end on, let me just spring ahead for a second. I just want to see if I want to start. No, okay. So on Monday, we're going to finish up with the last portions of these 5 more slides. The reason why I'm stopping here is because we're going to talk biological issues, and we're going to talk about safety and measurement. Okay, so those are the last big pieces of this chapter. What we shall do, I'm going to send you this PowerPoint with the pretty pictures. Just so you have it. I'm going to send you the cheat sheet. It may have more on it than we've covered tonight, but I just want to get it out to you so that you can study it and look it over. And then on Monday, we'll go right into like biological radiation effects, tissue damage, critical organs, safety and measurement, and do math. I love math. I hate math. Just kidding. No, I actually hate math. I'm not even lying. It's horrible, but we'll get through it. We'll figure it out. Is there any questions thus far? We talked about a lot tonight. Radiopaque and radiolucent. Please know those definitions, what those look like, and what tissues are in the mouth of those, okay? Anatomically, huge. I want to make sure that you understand KVP, the ranges, MA, the ranges, those characteristics, what makes a good quality picture, the quantity, the intensity, like list them out so that you have that. And then that nice, the definition of contrast versus density. And then finally, those measurements of like, if we have high KVP, we need a lower time in MA, and then vice versa. So those are like the really big crucial parts of this area. When you go to take the exam from Danby, they ask a lot of those questions, okay? All relative, but they ask them in all different ways. What setting controls contrast? Oh, KVP. What setting controls density? Oh, MA. You know, what are the ranges? 65 to 70, 85 to 100, ideas like that. So I just, to kind of clarify those out. That is a wrap. You guys did great. It is like science class to Mia. It's exciting.
I have a question.
Yeah, give it
Are
to
we
me,
gonna
Kristen.
have like a quiz on all of this vocabulary? Like, how much are we gonna cover
Yes.
before? Because I got 4 kids,
Yes.
2 dogs, and a whole bunch of stuff. I gotta fit it into my schedule.
Oh my God, girl, I hear ya. I wasn't gonna scare you. I was gonna on Monday when I conclude, every time I conclude a chapter, I send over the cheat sheet and I give you guys a review test.
Awesome.
I
Thank
don't
you.
grade you because, I can't grade you, but we go over it and then you
Okay.
can use that as a study guide. Yep.
Awesome. Thank you so
Yep.
much.
I love
Not a
that.
problem. Not a problem. Yeah. So, and what I try to do is end things on a Monday, so you have 2 days to do the little review test, and then on Thursday we can review and then start a new chapter, and then you can start studying over the weekend. That's typically my spiel. Sound good?
Thank you.
You're welcome.
All right.
All right, all right, all right. Here we go. Oh, Bree, you need to smile. I'll see you in the morning. I'm gonna take some
You're
pictures.
gonna be there tomorrow?
I am.
Yay.
For the next forever. I'll be there. Yeah, I got you, girl. I got you. All right, everybody have a great weekend.
Thank you. Have a good one, everybody.
You
Bye.
too.
You too. Have a good one.